what is the difference between the fluid and the solid, right? When you apply forces on solid, what you get, a certain amount of strain is obtained when you apply a certain stress, right? Suppose this is a solid, you apply a stress, you get strain out of it, right? As simple as that. But it's not like in the every case, in the case of fluid, it's not like that, because the fluid, the shear rate, which we can say, or the proper word we can say shear strain rate, is going to vary like throughout the fluid. A fluid is called as a continuum, right? I will let you know why it is called as a continuum, because when a viscous fluid is flowing over a surface, it forms a continuous layer, and therefore it is called as continuum. But the thing over here is that in the fluids, the shear strain have different shear strain rates of different values. And for the given shear strain, it changes with respect to time. So we can say the shear strain which is produced is time dependent. Therefore, in fluids, the rate of shear deformation is quite more important than the normal deformation which we see in the case of solid. So yeah, we will be studying about the properties of it, and the very first property which we are going to deal with, or I can just write it here in terms of tau, or if we talk about the shear strain, just to give you an idea that the shear stress is applied on a body is directly proportional to the shear strain produced, right? And to be more clear, it can be also mentioned as the rate of shear strain, d psi by d. Okay, this is for the any body, and it depends upon a property which is called as viscosity. You have heard about viscosity. Viscosity is the property on which basically this properties of application of stress and the shear strain, it depends a lot. Okay, so we'll be talking about the shear strain in detail, and we'll be talking about the Newton's law of cooling also, or Newton's law of viscosity related to it. So the term which we are going to talk about is viscosity. Now, in a simple term, do you know what viscosity is? Amin? Hello? Hello, Amin, can you hear me? Yeah, yeah. So yeah, just you know the meaning of viscosity. Like, have you heard about the property viscosity? Exactly. In a very simple way, it can be mentioned that it is the property. It's a kind of resistance which is offered when a liquid is flowing, right? And just to understand that in very detail, that how it is related to shear stress, let's assume that this is a plane body on which a certain liquid is flowing, right? Suppose a liquid is flowing. Let's divide this liquid in different layers. Let's say this is the layers of the liquid. And we are assuming the flow as of now to be a uh, the flow to be a laminar flow, which means that it will start with a point where the velocity will be equivalent to zero, and it will reach to a point where the velocity will be, let's say, 99% or approximately equal to the critical velocity, right? The critical velocity is a velocity which is required to maintain a continuous flow of a liquid. Now, as you see, with the increase in the height, let's say this y, or in a very let's consider it as height only initially. Now let's say this height is y, and with the increment in the on increasing, right? And it will achieve a maximum value, let's say, which is 99% of the critical value at a certain height y. And this distance over here, what we are covering, the stepwise distance we can observe that every increment in the distance, the velocity is going on increasing, right? So what happens is that, let's consider two layers. Let's consider the layer one and the layer two of a liquid. What happens? This layer, it obviously the velocity is going on increasing on the upper hand. Then this above layer will try to pull this layer towards itself, right, in this direction, and which will be opposed by the layer two due to the cohesive force between these two layers in the downward direction. And what happens due to this type of stress acting two in the opposite directions, we see the deformation happening at the surface, right? And this property is indirectly called as viscosity. This property is called as viscosity. Okay, and again we can just relate this viscosity to a in terms of shear stress with the Newton's given normal formula that this let's initially start with viscous force. Now this viscous force, let's say it as F, is directly proportional to the area. It is directly proportional to the velocity gradient as well. The greater will be the velocity gradient, and the greater will be the force application over there, right? So it will go on increase with respect to the velocity gradient. And if I relate it together, I will get F is directly proportional to A into dV by dy. dV is the change in velocity, y is the change in height. This can be together called as the velocity gradient. And if I relate it, I can write it as F is equal to mu into dV by dy into area, and this dV by dy is called as the coefficient of viscosity. Coefficient of viscosity, right? And again, if I just arrange it, I can write that F by A is equal to mu times du by dy, which F by A can be represented as shear stress is equal to mu into du by dy. And if I relate the, let's say this term, number one term and number two term, what I am getting in this case that this thing du by dy is nothing but a shear strain rate. Okay, so this du by dy is nothing but the shear strain rate which is happening over there. In the numerical terms, these both values are equal. Is this clear? And the opposite of mu is called as the fluidity, the reciprocal. Fluidity. Fluidity is the reciprocal of the viscosity offered by the body. Okay. And if we just okay, you first write down this thing, then we'll move forward. Write down this thing. Yeah, F is proportional to A exactly because this is the area. The greater will be the area in contact, the greater will be the cohesive force and greater will be the resistance, right? Got it? Yeah, like generally like we are right now considering a particular small section, but overall when we study the area of a fluid is going to remain very infinite, right, and very long. So it will be nearly same for each. Yeah. The last term, basically, what do you mean by last term? This or this fluidity part? Here we have related it because here it's a proportionality sign, right? So proportionality sign is equal to like d mu is equal to some constant k into d phi by dt, right? So we have just related d phi by dt. Now, if we just try to talk about few questions related to it, like we know that the tau is directly proportional to, let's say, d phi by dt, and then you came to a conclusion that y is phi is equal to du by dy. If I just draw the part in this case, you can relate this equation as y is equal to mx, which is the equation of straight line passing through the origin, right? And greater will be the m. The greater will be like, let's say the theta will be more greater, right? Tan theta basically represents the slope. So greater will be the value of slope, the greater will be the angle made with respect to the x-axis. So if I write this as my x-axis and this as my y-axis, and if I plot 3 points, let's say y1, y2, and y3, each operating from the origin, let's say mu1, mu2, and mu3, then definitely mu1 will be greater than mu2 will be greater than mu3, okay? And if I talk about the units in this case, so this the thing, there are like two types of viscosity. The first thing which we are going to talk about is the dynamic viscosity. Now, dynamic viscosity is the general viscosity which we are seeing in this case, which is represented by mu. Okay, and the unit for the mu, the SI unit basically for the mu is, you can just go from this Newton meter square per second into second, Newton second per meter square, and you can just relate it with this, and you can move that way. And in some cases, it is also called as absolute viscosity. Absolute viscosity. Okay, is this clear? And if I talk another type of unit related to viscosity is the dynamic viscosity. Okay, and you can just write it as Pascal second as well if you want. It's Pascal seconds, right? This mu can also be written as Pascal seconds, and you can also relate it to if I just select another unit which is poise. Poise is the general unit. Okay, so one poise is equal to 0.1 Newton second per meter square. Okay, and you can also write it is equal to 0.1 Pascal seconds. Okay, and this is how you can relate it. And if I talk about the second quantity which is related to viscosity, it is called as kinematic viscosity. Kinematic viscosity. I could talk about the term kinematic viscosity. What do you understand by this term in a very simple way? It is actually the ratio of dynamic viscosity to the density of the body, right? It is denoted by this way. And is the ratio of, let's say, the kinematic viscosity with the dynamic viscosity with respect to density. And if you want to write the ratio of this, it will be basically divided by meter kg meter square by, okay. So basically we'll get meter square per second as the unit. Divided by kg per meter given, then you can go that way. And this is the SI unit. And another way in which the kinematic viscosity is measured is Stokes. It is also a very common unit. Whenever Stoke is given, understand they're talking about the kinematic viscosity. And just to relate it, I can write that 10 raised to power, let's say 4 Stoke is equal to 1 meter square per second. Okay. So this is the relation over there. And you can just relate it as in a very simple way as like the value. If you want to write the Newton's law in the terms of this, you can write that I is equal to mu du by dy. You divide by density, multiply and divide by density on both the sides, you will get tau can be written as the kinematic viscosity into density to change in velocity up with respect to the gradient height. Okay. And if we talk about the effect of temperature on viscosity, so basically we'll be dividing this viscosity section into two parts. Listen very carefully here. Okay, let's take one part as liquid and the other part as gas. Okay, generally viscosity is our fluid property. Basically, it is liquid, and all those materials which flow will show you the fluidic property, and liquid and gas both flow, right? Now, in the case, what happens when we have liquid with the increment in the temperature, what will happen to the cohesive force? I mean, it will decrease or it will fall down with the increase in temperature. What you will see? What will happen to the cohesive force? Exactly, it will decrease. It will decrease because the intermolecular distance between those gases is going to increase, and as the cohesive force goes on decreasing, obviously the viscosity will go on decreasing, right? While in the case of U gas, uh, what we can say, uh, the temperature, with the increment in the temperature, what happens to the velocity of the gas? Because whenever temperature is imparted, this molecules, obviously cohesive force is not an action in this case. With the increase in temperature, you will see the increase in velocity. Why you see increase in the velocity? It's overall, if you see, there is a decrease, like the velocity of the increase, the velocity does not change much, but basically in the case of gases, we deal with RMS velocity, right? So this RMS velocity increases. This because number of collisions can increase with respect to this with the increment in the temperature, right? And therefore, and if you state a relation in this case, it's a relation is sometimes that obviously this temperature is increasing, the velocity is increasing, your the viscosity will also increase, and the relation is basically the mu for the gas is directly proportional to root 2 times the temperature at which we are talking to it. Okay, and this is how you can relate it. Yeah, write down this terms. Yeah, okay, let's move forward. Yeah, we're done writing, and we will be discussing about the types of fluid. Like this fluids, depending upon this type, are further classified into two, three types. So basically, mainly two types: the one which obey the Newton's law, and the other which do not obey the Newton's law. Right? So they may be classified as Newtonian fluids and non-Newtonian fluids in general. Okay, so this fluid are then classified into two types: Newtonians and non-Newtonian fluids. Okay, so what do you mean by Newtonian fluid? In a very simple way, they obey the Newton's law of viscosity. Non-Newtonian do not obey the law of viscosity. Now, what does it mean is that understand very clearly that for a Newtonian fluid, what we see the relation between the shear stress and the du by dy was a linear relationship, right? In a very simple way. But in the case of non-Newtonian fluids, they are further, let's say, classified into two more types. Okay, they are further. Let me just write it very clearly so that it will be very clear to understand. So, fluid, they are classified into two types, right? These are Newtonian fluids in which the tau is directly proportional to du by dy, right? But in the case of non-Newtonian fluids, the relation is not linear. Apart from that, they are also dependent upon non-Newtonian. So basically, they are the function of the viscosity over here is a function of the time as well as the velocity gradient. Okay, so they two are following the same relation, and depending upon this, they are further classified into two types of fluid. The first one are basically called like are further divided in the first one, which is like they are not dependent upon the time, means they are dependent upon the velocity gradient, but not necessary that these velocity relation would be a linear relation. Okay, so which leads to a three cases over here. The three cases over here are the dilatant, okay, then pseudoplastic, and then Bingham, or you can also write it as ideal plastic. We will be talking about this in detail in Bingham. Okay, while here these are classified into two types: the thixotropic and the rheotropic. Okay, in this case, what we see that these are a function of time. This varies, the viscosity varies as a function of time, and they are two classified as thixotropic, and the other one over here is called as rheotropic. I'm writing it down over here. Rheotropic. I'm again writing a name. Look at very clearly what the things are. Now, if you talk about the Newtonian fluid, the graph was very simple. Then let's say this was your tau and this was your mu. It showed a straight relationship. No, sorry, this was du by dy, right? Velocity. It showed a relationship like this. Now, in the case of the other fluids, uh, you can just draw the graphs like in general. If I draw the graph, right, and or let's do one thing before drawing the graph. Let me just give you an idea that how this thing, how this. Oh, let's first draw the graph, then you can go towards the idea part so that we can discuss it again. Okay, so let me draw all the fluids here. So this straight line represents the Newtonian fluid. Okay, here you have tau, and here you have du by dy. So this thing over here will be your dilatant. Now, dilatant are the one which are not dependent upon time. Dilatant, okay. And again, this is your pseudoplastic. This is pseudoplastic, okay. And this one over here will be your this is the general thing over here. And if I relate it further on, let's try to extend this line further. Now there will be a certain height over here, this part, tau I intercept of tau I over here. Now this one is going to be a Brigham. This one is going to be your thixotropic, and this one is going to be your rheotropic. Okay, this is the relation we have drawn between tau and what is in the case of ideal fluid. This ideal fluid, this is this line, this straight line over here. This is what ideal fluids are. They do not show any kind of viscosity. Okay, and if you want to draw it with respect to time, okay, if I draw this graph with respect to time, you are able to understand it. I mean, this is your view and this is your time, and if you try to draw this with respect to time, see, this is a constant, they are not going to vary with respect to time, and then this is your rheopathic and this is your thixopathic. So rheopathic, this is your thixotropic, and the time dependent, like they're independent of the island, pseudoplastic and granular. So you just draw this graph very clearly, and the equation which we are governing all this, the equation is very simple. The equation can be written as basically the general equation how this with the related is tau should be equal to, you know, y is equal to mx plus, you will be writing in this form. So let's say this is your m, this is your x part raised to power n plus b is the y-intercept. So on this basis of equation, we will be deciding the further things. So you write earlier, then we'll be deciding the further things. What are the things?